Hi folks, welcome back to Physics with Captain Rod. The purpose of this video is to help you out with one of your homework problems here. We're going to talk about what is currently 6.4 in your textbook here. And in this example, there's this object free to rotate. At t equals 0, it's rotating at 12 radian per second, and it's got a constant angular acceleration of 20 radian per second. And what they're asking you to do is essentially find the velocity and acceleration of this point B after this has rotated through 2 revolutions. So if we imagine, what B is going to do, if I did like a motion diagram, B would be, might during one little delta t, it might be like here, and another delta t, it might be here, and another delta t here, and so forth. So as this thing moves around in the circle, B is going to be moving faster and faster and faster. I'm going to put some vectors on here too. The velocity vector at the instant shown, so I'm just going to imagine at t equals 0, B was here, and then after 2 revolutions, it's right back to the same spot. The velocity vector I'm going to put in green might look something like this. And the velocity vector can be written r times the angular velocity, if we can find that, and we should be able to find that, no problem. Now, in addition to that, we've got acceleration vectors. I'm going to put those in red. There's a tangential acceleration that's going to be this way in the same direction. But there's also going to be a centripetal acceleration, which is going to be towards the center of curvature. The tangential acceleration can be calculated by r times alpha, and I think we have that. The centripetal acceleration, is equal to v squared over r. That's also equal to r omega squared if you just put v equals r omega right here. So we're going to have to find the angular velocity to answer both of these questions, here and here. Tangential acceleration we can just calculate right now. I'm going to go ahead and do that. So the tangential acceleration of B is going to be, well, actually, this is your problem. The r is given, and the alpha is 20 rad per second. To get the centripetal, we're going to need the rotation rate. And also, to get the tangential velocity, we're going to need the rotation rate. Before I talk about how to do that, let me go back and comment about the picture. In green here, this was the velocity vector. The velocity is tangent to the curve. I drew the other vector shorter, well, for really no reason at all. It doesn't even make sense to compare the magnitude of an acceleration to the magnitude of a velocity vector. So the fact that this is shorter has no, there was no meaning behind that. Another thing you'll notice, I drew the tangential shorter than the centripetal. Again, I don't know the relative magnitudes, so I just guessed. In all likelihood, the centripetal will probably be larger. Usually what happens is centripetal accelerations very quickly become the dominant factor in a problem. Now, to get the both the centripetal and that tangential velocity, we're going to need the rotation rate. So I'm going to do a quick little graphical analysis of the motion of this object, or I'm going to, what you should do. And draw a graph of the angular velocity against time. Keeping in mind it started at 12 radian per second. It's got a positive slope, and this is going to go out to some time, which right now I'm going to say I don't know. But since we know the slope, you should be able to find an equation for this line. Keep in mind the intercept is 12 and the slope is the angular acceleration. Once you do, this area right here will equal the change in theta. Now, that should allow you to write an equation fairly easily for t. You can either use integration or just use the area under this curve here. Either one, either way will give you a nice, fairly easy equation. That'll get you the time. And once you have the time, you can go back to this equation here for this to calculate the angular velocity. Once you have the angular velocity, that value can go there to get the centripetal acceleration, and it can go there to get the tangential velocity. So that should be enough to get this thing done. Maybe wondering, how do I know what this area is equal to? Well, the angular velocity is d theta dt. And if you separate that, that's going to read d theta equals the angular velocity times dt. So the angular velocity times time is giving me a change in angle. And on this picture, the angular velocity is this dimension, the time is this dimension. So the product of the two is giving me an angle. Also, when you write that equation, this delta theta is given in revs. When you write this equation, you're going to want to use 4 pi radians. So that should be enough here to help you out with 16.4. I think I'll just end this video here and start another one. Have a great day.